Good afternoon, everyone. This is another ARC seminar, and today's speaker is Dr. Moumita. She's Honorary Research Associate at UKZN, and she'll be giving the seminar on cross correlations with HIRAX. Moumita, the stage is yours.
Hi, thanks, Ajit. Hi, everyone. So I'm going to talk about cosmology with HIRAX. So I'm going to show you some results on combining like 21 centimeter and large-scale structure surveys. So I'm not sure what the general audience would be like, but I'm pretty sure there's at least people at UKZN have heard about HIRAX a lot. So depending on, yeah, I can see Tony's there, Shavara's there, and Ajit. Obviously, all of you work on HIRAX, and if you don't work, you definitely know about HIRAX. So what I'm going to do is I have a few basic slides. I'm just going to go through them quickly if there are any students who would like to know the basics. Okay, I'm not sure what's happening with my slides. It's not moving. Okay, let's see. Okay, there you go. Okay. What we're doing is we're doing astronomy in the era of big surveys. So the way we did astronomy compared to a few decades ago is definitely changing. So what we are looking at is like big science. So basically you have big surveys, and all these big surveys have big data sets, huge collaborations, and obviously you need a lot of people, so a lot of questions, budgets. So I've just, this is obviously not an exhaustive list of all the astronomy big surveys which are happening. So you have Euclid, you've got WFIRST, which is known as the Nancy Grace Roman Space Telescope. Obviously, you have the Square Kilometer Array in Kourou. I've put a LSST, which is now known as the Vera Rubin Observatory, because that is one of the experiments which I'm going to talk about. So the reason why we need such big surveys is basically there are a lot of things which are still unanswered, like what is dark energy. We know a lot about inflationary models, but we don't know if inflation is actually real or not. We also want to answer things like where does general relativity break down? And then we can obviously question what is like dark matter, does it exist, or if there's something else. So to answer all these big questions, what we need is more data and like map of how the matter is distributed throughout space-time, information about how structures grow, and obviously we have like observations on like billions of galaxies across cosmic time. And that's the data which we are going to collect from these big surveys. And then we might need new ideas, new theories on how to explain these observed phenomena. So a brief introduction to radio cosmology. Okay, so the radio is why we look at the sky in radio is because it is very different to any other wavelengths. So this is an example. This is a diagram which is shown in like astronomy undergrad courses. So you have something known as the windows, atmospheric windows. So you have like the radio window, as you can see. This is basically quite a clean window. So this is showing you the transparency of the atmosphere. So yeah, so you can easily do radio probe Earth, and yeah, it's quite a clean window. So you have a lot of high energy physics in radio astronomy. So you basically looking at black holes, neutron stars, pulsars, supernova. As you can see from this atmospheric window diagram, that it doesn't get absorbed easily. So when you're looking at, say, neutral hydrogen, the radio waves emitted by neutral hydrogen, they pass through the dust and the gas quite easily. And this is an efficient way of seeing hundreds of millions of galaxies that trace the large-scale structure of the space-time. Right, okay. So again, a very quick view of why we need radio. So this is what you have. Cygnus A, now it's known as one of the largest, strongest sources of radio emission. So if you look in optical, I couldn't find the JWST image for Cygnus A, but yeah, this is something which you see in HST. So you can see it's quite pretty, but a lot of there's a lot of missing things which you cannot see in the optical. So this is what you see with Chandra. That is the X-ray emission from Cygnus A. So you can see these blobs and the X-ray gas around them. And then if you look at radio, so this is using NRAO and VLA. So what you can see is these powerful jets emitted by most probably a quasar at the center. So this is what you see in the radio. So as you can see that radio, not necessarily just radio, other multi-wavelength astronomy is necessary to see the more composite picture of structures in the universe. And this is the composite picture of the optical, the radio, and the X-ray for Cygnus A. Right, so as I said, the sky looks different in different wavelengths. So this is just the full sky view of the full view of the sky using different wavelengths. So you have the Fermi satellite, the gamma ray. It's a gamma ray telescope. You've got Gaia, which is one of the optical missions. You've got radio, you've got microwave, you've got infrared, and then finally radio here also. So these two are microwave. This is radio. Right, okay, so let's kind of move on to what we are going to talk about. So this is like the customary picture in any cosmology talk. So you can see the timeline of the universe. This was created by the WMAP team. So we are going to look at the timeline of the universe. We are going to concentrate mostly in this red box here. And like I'm going to talk briefly about this red box here, which is basically the last scattering surface. So why are we talking about the last scattering surface when we are talking about when we're in a talk for 21 centimeter is mainly because we need to know a little bit about the CMB. So I'm not going to have any introductory slides on the CMB, just to tell you that the CMB, the cosmic microwave background temperature and polarization, that is from this this era. So this is the surface of last scattering. So the CMB power spectrum, this is what you have, the power spectrum. So you've got the temperature power spectrum marked in black. And you can see the polarization power spectrums, so the E modes, which have been measured. And then you have the very elusive B modes at large angular scales. So these are basically the signatures of inflationary gravitational waves, and these are yet to be discovered. Right. Okay, so this is just like one slide on CMB. And why are we talking about CMB? Because we need to talk about baryon acoustic oscillations. Okay, so the baryon acoustic oscillations, these are just the primordial density fluctuations generated during inflation. And so what happens is it's like basically like combination of gravity and pressure waves in the early radiation dominated universe. So what happens is you can see here, so just imagine there's like one single acoustic wave. It's propagating in the coupled baryon photon fluid. And when these photons decouple from the baryons, they leave the imprints of these waves as the relic radiation, and that is what the CMB fluctuation is. And so what happens is the same acoustic waves, which are at the last scattering surface, they leave an imprint on the matter fluctuations, which you can see later on, because that's where large scale structures will later evolve from. Okay, so that is why we talked about the CMB and then the BAOs, and again just a simulation of how from BAOs you get to the CMB. So basically, you saw this was just one fluctuation, and that produces something like this. But if you have multiple ripples like this, what you get is a combination of all these circles. And so the combination of all these circles is what you see as the CMB. Okay, so this is what you see as the CMB finally. So this is a CMB, as part of a CMB full sky map from Planck satellite. And the red and blue dots basically are just temperature distributions. So the red dot is like a hot spot, and the blues are like a cold spot. So basically just showing you the temperature distribution of the CMB temperature distribution. Right, so this is how we get from the baryon acoustic oscillations to the CMB and galaxies. So the imprints left by the baryon photon plasma oscillations prior to decoupling, That is, this is basically the CMB. This is just the temperature power spectrum from Planck satellite. But as we said, that these propagate later on, and they form the, that's where the large scale structures form from. And you can also see that in the matter power spectrum. So what you can see here is, this is basically the effect of dark matter and visible matter. So that's the galaxies during structure formation after decoupling. And you can see this tiny bump, which is enlarged here at about 100 megaparsec in the H inverse. Co-moving separation. So that's the signature of the BAOs. So you can see the signature of the BAOs in the matter power spectrum as well as in the CMB temperature fluctuations. Right. So now we come to cosmology with BAOs, and BAOs basically, they provide like a standard ruler. So what's happening is you're measuring, so the same co-moving length scale is observed over many epochs, okay? And the observed angular scale over different redshifts, they provide a geometric measure of the expansion history, right? So this is how you can actually measure dark energy using the BAOs, because this is particularly important at this redshift between 0.8 to 2.5. That is where dark energy dominates. So you can use BAOs as a geometric measure of the expansion history, and you can measure dark energy constraints using BAOs. Okay, so this is just a figure from 2013. So this is a bit old, but yeah, so this illustrates quite clearly that the current BAO distance redshift relation, which you have from different experiments like got SDSS, BOSS, Wiggle Z. And so, yeah, so this is basically why we are looking at BAOs to measure like dark energy constraints, because that's what HIRAX is going to do. Right, so let's come to HIRAX. So basically probing dark energy with BAOs using 21 centimeter intensity mapping. So we have explained what are BAOs. I'm not going to explain about dark energy, but that's what we are trying to probe using HIRAX. So what I'm going to explain now is the 21 centimeter hydrogen intensity mapping. And again, this might be a repetition for a lot of you, but for completion, I'm just going to quickly go over it. So the 21 centimeter line, it's nothing but it comes because of the spin flip of the hydrogen atom. So the hydrogen atom, so what happens is if this basically flips from being parallel to anti-parallel, what happens is the energy difference is equal to h nu, and nu is equal to 1420 megahertz. And the frequency corresponds to 1420 megahertz, and that corresponds to a wavelength of 21 centimeter. And that's where we get the term 21 centimeter. So 21 centimeter or 1.4 gigahertz, that is, it's becoming, this line emission is becoming a powerful tool in cosmology. And the reason why it's becoming so popular is also because hydrogen is the most abundant element in the universe, and you don't get any confusion from other emission lines. Right, and it's a forbidden transition of the order of 10 to power 10 mega years lifetime. And when you observe the frequency, that gives a very good measurement of the redshift just by using the redshift equation. So if you are measuring it at a redshift Z, and you observe, you will observe the wavelength at a, say, the frequency of the wavelength should be nu observed, and 1420 is basically the wavelength of the spin flip transition, right? So this is the equation. This is the equation which we need for 21 centimeter cosmology. So we can use 21 centimeter line to study the history of matter and growth of structure in the universe. So as you can see, this is basically telling you the brightness as a function of the frequency and the different eras which you have here. So epoch of reionization starts here. This is where the first galaxies form. So yeah, so that is why 21 centimeter is considered to be a very good probe for studying the history of matter and the growth of structure in the universe. Right, okay, so let's look at 21 centimeter intensity mapping. So if you want to study BAOs using 21 centimeter intensity mapping, Firstly, what you need is, if you remember, the BAO scale is about 150 megaparsec, right? So what you need is large volumes. You need the large sky, large redshift range, and that is obviously a requirement for precision cosmology. So if you need something of the order of the BAO scale, so like 150 megaparsec, you need a large spectroscopic survey. And what happens is, in this kind of a survey, counting individual galaxies become very challenging. And counting them at high redshift is very challenging. So that is the key thing why we need to move on to something called intensity mapping. Okay. And the other reason is, even though hydrogen is abundant, the hydrogen 21 centimeter line is very faint. So it is hard to just observe, for example, say an individual hydrogen 21 centimeter line. So instead, what we do is we use this method called stacking. So you stack up the signals from many galaxies, and you don't need to measure them at very high resolution. So you take low resolution surveys at different redshifts, and then you just combine them. So that gives you a higher signal to noise also. And so that is what is kind of a very basic introduction to what is H1 intensity mapping, to measure the matter distribution and obtain the redshift information. So this is just a very nice summary of what I said. Like, what we are trying to do is we are trying to measure H1 emission lines from different galaxies. And as I said, it is actually the 2170 lines are weak, and the signal is weak. So what you need to do, so you can see it gets redshifted when it reaches the telescope. So what you're trying to do is measure, basically look at the region of sky, measure the 21 centimeter from that region of the sky, then move on to a different redshift, and then again measure the emission from there, then move on to another redshift. So basically you measure it in different redshift bins, and then you stack it out. And that's how you get a higher signal to noise. Right. So as explained again, what you have here is a collective emission from a large region, okay? And what you don't need to do is spatially resolve down to galaxy scales, okay? And then what you're doing is integrating all the photons from the dim sources. Then you measure the brightness temperature fluctuations. And what happens is, because you're using these spectral lines as tracers of the structure, you can retain high frequency resolution, which will lead you to the redshift information also. So this is, for example, showing you what an intensity mapping looks like. And this is basically looking at individual galaxy. You can do a combination, and that's what the combination looks like. Right. Just to show you how powerful intensity mapping can be, for example, what you have here is a 2.5 degree square field with galaxy positions. That's the left map. And on the right, what you have is a CO intensity map from an experiment called COMAP. So this is an intensity mapping experiment. This is using VLA with 27 radio dishes. And I think the time is about 4,500 hours. And what you get is about 1% of the total CO emitting galaxies. And this is using COMAP, the COMAP array for 1,500 hours. What you can see is it produces a map of intensity fluctuations sensitive to emission throughout the field, and you can kind of point out where your emission is coming from. Right, okay, so again, like, these are the different 21 centimeter experiments. And again, this is kind of like a timeline of the universe. And I've marked LSST again because that's what we are trying to correlate with. Yeah, so I think I'm going to quickly move over to what HIRAX, the slides on HIRAX. So again, intensity mapping. The other thing which I didn't talk about is foregrounds. Foregrounds can be removed by filtering in frequency. The reason is foregrounds are quite the H1 signal has more structure compared to the foregrounds. So but the thing is, as you can see, that the foregrounds are actually much higher than the signal. So there are some issues which we are going to talk about. Let's move on to why we're looking at H1. So, okay, this is just basically showing you the first detection made comparing H1 maps to galaxy maps. So this is kind of also a motivation of why we are trying to cross-correlate H1 and, say, other things like optical or galaxy density fluctuations. So this was the first detection. So this is the, sorry, I don't have, the references here. Chang et al. 2010. What they measure is basically omega H1 BH1, and this is like a cross correlation coefficient. So what you have here is the galaxy bias coming in and the H1 bias coming in your total cross correlation power spectrum, the H1 and the galaxy power spectrum. So this is basically a measurement, the first measurement of H1, but it's measured in a cross correlation. Right. Okay. So this is basically where HIRAX comes in. So HIRAX is basically going to try to measure BAOs using intensity mapping within the frequency range of 400 to 800 megahertz. So that corresponds to redshift 0.8 to 2.5. So that's where dark energy dominates. So basically, we're trying to capture the dark energy parameters also. Right. And it's got yeah, I think in the next slide, I have all the channels. So HIRAX is basically a hydrogen intensity and real-time analysis experiment. It's also the name of a California punk rock band, but also a homonym of the rock daisies found everywhere in South Africa. And this is basically the specifications for HIRAX. So it's between 400 and 800 megahertz, basically to capture the redshift range for dark energy. Yeah, the dishes are like 6 meters in diameters. Yeah, so that is basically the HIRAX specifications. The location of HIRAX will be somewhere in Losberg, so in the Karoo Desert in Losberg. I think the prototype, I haven't joined into any of the telecons in recent times, so I'm not sure what's happening at Hartrau. So there was a prototype, and Tony and Ajit can obviously tell you in more details with what is happening at the prototype. Let's move on to, okay, I'm gonna skip through these slides because I don't want to, so this is just basically telling us that HIRAX is kind of complementary to CHIME, which is in Canada. But here is a few comparisons, and the reason why HIRAX is obviously in the Southern Hemisphere, and most you will see in a figure which I show later, most of the other surveys like CMB surveys or optical surveys, LSST specifically, they're also in the South. So the cross correlation, which we're going to talk about, helps with foreground mitigation. So HIRAX is definitely going to be useful that way. Right, okay, so yeah, I'm going to skip through these slides because I'm pretty sure there's more recent slides, and I'm going to move on to, so this is basically just showing you some of the cosmology, early cosmology, which was done by Devin. Just cosmology, so basically the dark energy parameters are constrained here. And then you have, yeah, this is basically the BAO power spectrum constraints, which you can get from HIRAX. So with the 128 element, and then 512 and 1024 element. The other thing which HIRAX is going to do is basically being used for fast radio bursts. And Tony, I thought I saw his name, and he's an expert on that. Basically, what the plan is to basically have different stations, different out-trigger stations, sorry, at different places. So basically, you get long baselines for VLBI positions, and yeah, so you can contain basically the location for the fast radio burst. Right, let's move on to cross correlations of HIRAX. So there's a lot of people working on cross correlations with HIRAX in general with radio and CMB and radio and optical surveys. So I'm going to talk about HIRAX and optical surveys. So what you see here is, because of HIRAX's location, as I said, as you can see, a lot of the experiments are actually based in the Southern Hemisphere. So this just shows you the LSST survey region. You have the other CMB experiments also, like Advanced ACT. So that's the observable sky. South Pole Telescope is also there. You also have the dark energy survey. Yeah, and so again, as you can see, the overlap HIRAX is basically shown in this gray block here. And you've got CHIME basically is the southern extent is shown as in this bit. And then you've got MIRCAS, you've got Advanced ACT Pole, as I mentioned, you've got LSST and so on. And these are some plots using HIRAX and say Planck, with HIRAX 256 dishes and HIRAX 1024 dishes. This is from a paper which was published in 2021. And this is from what I'm working with Warren and Covey. So this is basically using HIRAX, but different autocorrelations, cross-correlations, and a bispectrum, which I'm going to talk about just now. And so we're trying to constrain the dark energy parameters using various orders of spectrums. Right, okay. Let's move on to the cross-correlations of HIRAX. So the reason, as I said, I already mentioned why we are interested in radio-optical cross-correlations, because the first detection of 21 centimeter intensity mapping signal was done in 2010 using the GBT and WiggleZ survey. And this is something which I showed before. So that is basically one of our main motivations for looking at radio-optical cross-correlations, because you can measure the 21 centimeter signal in cross-correlation. Also, it provides complementary physical constraints because you have different probes, so you can measure different things. So like, for example, cosmological probes, you can measure like clustering, BAOs, redshift space distortions, lensing. So that can be done using cosmic shear and convergence. You can also have growth probes with the RSDs as well as lensing, or expansion probes with BAOs and lensing. So the cross-confirmation of results and mutual support also is a key motivation in our case for looking at radio-optical cross-correlations. So for example, when you look at Rubin LSST, LSST is going to provide the photometric redshifts for H1 continuum survey, but you can use the redshifts which you can find in HIRAX survey. You can calibrate the LSST photo Zs using the cross correlation. So this is kind of like the motivation, and you can go on, like obviously it helps in removals of systematics when you cross correlate the two, foregrounds, noise, and systematics are a big challenge for intensity mapping. And like the first detection of H1, as we said, it was done using cross-correlating GBT and WiggleZ. The foreground challenge can be mitigated in some cross-correlation surveys. Right, and there are obviously other things which we can talk about, but I'm just going to leave it out here because there's obviously there are other things and I don't have time to talk in details about these ones. So I'm just going to talk about one of the other results which we had from the team at UKZN. So Heather, Orally, Covey, Warren, and Covey, they had two papers on CMB lensing and intensity mapping. So the convergence and the shear CMB lensing, the convergence and the shear cross correlations, so they have a good overlap with the intensity H1 kernel, as you can see here. So because of this overlap, you can actually do cross correlation. So that is something which you can do. And if you're interested, please have a look at their papers. So what we are doing here in our paper is we're talking about shear and galaxy density cross correlation with H1. So two key probes from the Rubin LSST dark energy program is the cosmic shear and the baryon-acoustic oscillation signature. So what we are doing is, and obviously we have the H1 intensity mapping survey from HIRAX, and that's a bias tracer of the large scale structure. And that is going to correlate with the galaxy, which basically is tracing the stars, and the shear distributions, which is tracing the dark matter. So this is what we are doing here. We are correlating the galaxy density with H1 and the shear distribution with H1. Right? So this joint power spectra, this will probe neutral hydrogen, stars, and dark matter, and it will also break certain parameter degeneracies which are present in a single probe, and I'll show you how it manages to break the parameters. Right. So just a single slide on the Vera Rubin Observatory, which was known as the Large Synoptic Survey Telescope. So this is a 10-year survey of the sky to probe like dark matter, dark energy, and obviously it has other goals. So it's basically it has 6 bands between 320 and 1050 nanometers, and it has got a large field of view of about 10 degrees. I think operations have already begun, so I need to change that. Right. Okay, so so the specifications for Rubin LSST and HIRAX. So HIRAX specification, what we are using is the total area we are taking is 15,000 degrees square, and we are taking the time for observation as 4 years. That is the redshift range we are interested in. Basically, that's what HIRAX covers. And what we have here is the Rubin LSST gold sample galaxy number count. So this is something which is important in our optical surveys. So this is just the distribution of galaxies over redshift. Okay, right. So these just show that the number of galaxies, the distribution in 1 year of LSST observation and 10 years of LSST observation. Right. So when we talk about intensity mapping, we need to talk about the Fourier modes. So Fourier modes, what happens is we split the K space into K perpendicular and K parallel. And so when we are looking at interferometers, what happens is there's some, I'm not going to talk in details about this. So what you have is basically a EOR window where you can basically get where the signal is high, but because the interferometers, they are like chromatic instruments with a given baseline. So what happens is you've got this foreground wedge, which we kind of need to eliminate or basically avoid it to get a good signal. Right, so let me just tell you what are the Fourier modes translate as. So as I said, the K modes are split into K perpendicular and K parallel. And in Fourier coordinates, they are also known as L and Y. So that is what we are going to use in our intensity mapping calculations, right? So this is just showing you the coverage in K perpendicular, K parallel for a single dish as well as an interferometer. Right. Let's come to, you'll see a few equations, so please don't feel too daunted by it, but it's just for completion, I'm showing you the different autocorrelations and cross-correlations. So here you have the 21 centimeter autocorrelations. What you have here is the brightness temperature fluctuation. That is the mean temperature. It's related with the H1 bias also. And you've got another term, F mu square. That basically comes because of the redshift space distortions. Okay, so F is nothing but just the growth parameter. There's the linear growth factor, sorry, and delta M is the matter density fluctuations. Okay, and again, you can write this in Fourier space, and when you project it in Fourier space, you get the denominator. So this is just consider this to be some projection factor when you take it from the Fourier space to the spherical harmonic space, right? Okay, let's see. Yeah, and then
I wonder what's the meaning on this slide. Parallel in the previous slides.
In the previous one.
Yes.
Here
you're no. Next one. The one with equation. Yeah. So here your K parallel equals y divided by r sub nu I. And what's the meaning of y?
So y is just L and y are the so that is basically taking you to the Fourier coordinates, right?
So what is like one-dimensional Fourier component? Y is one-dimensional Fourier component. Dimensionless.
Yes.
Okay, that's fine. Yeah.
Okay, right. Okay, so this is just the notation which is used in like the intensity mapping community. So that's why I just wrote it here so that you don't get confused. So K perpendicular, whenever you see L, it means K perpendicular, and Y means K parallel. So that's why I just put it out there. Right. Okay. So this is the autocorrelation. So you have the temperature distribution. So you basically take a 2-point function. Again, please, I think I just put it here just if anyone is interested. So again, you can see it's kind of like a square of this term here, what you have here. So it's nothing but you're doing a 2-point correlation of 2 instances of the brightness temperature, right? So that is what your autocorrelation is. And this is what you get. And this is what the noise looks like. So the noise power spectrum, this is what it looks like. NU, so this is nothing but a baseline density function. This depends on the interferometer you're talking about. It'll be different for different interferometers. And this is what the signal looks like, and this is what the noise looks like. And we've used the redshift bins for HIRAX to be such that the frequency difference is 100 megahertz. So this is how the redshift bins look like for delta nu as 100 megahertz. So most of our calculations are doing delta nu is 100 megahertz. You also have the galaxy and shear autocorrelations. So the things which are important to look at is the ones which are in the red boxes. So please just assume that what we're talking about in the galaxy autopower spectrum, it has something which is known as the galaxy kernel, which is the important thing. And that is what has the DNDZ. So the DNDZ is the distribution of the galaxies over redshift, and we take the value of the DNDZ as the LSST gold sample. And similarly for your shear power spectrum, what you have is the shear kernel, which looks like this, and G of chi is nothing but like the lensing efficiency kernel, and N of X is also related to DNDZ. So the things which are which you should be looking at is only the galaxy kernel, the shear kernel, and how it's related to the DNDZs, right? And this is also the shot noise power spectrum and the signal to noise ratio for X. X can be the galaxy and the shear. So this is what it looks like. So for both galaxy and shear, your noise power spectrum looks like a shot noise. Right, okay, so let's look at some figures. So if you look at the cross power spectrum between H1 galaxy and H1 shear, so this is what it looks like. And this is what is interesting is the signal to noise ratio. So if you look at the previous signal to noise ratio, so you can see that the signal to noise ratio is about 900 for one of the bins. Let's say 800 for say the bin between 1.37 and 1.84. But when you do the cross correlation, the signal to noise actually reduces quite a lot. So this is the thing which is the problematic thing, because whenever you do a cross correlation, the signal to noise decreases. The reason for the decrease in signal to noise is because what the kernel, the galaxy kernel or the shear kernel looks like in Fourier space. So you can see that it actually falls off quite quickly, okay, in k-parallel space. So when you're doing the cross correlation with galaxy and 21 centimeter, that is why your signal actually falls quite quickly. Right, so you can also see it from these plots. So this is the 21 centimeter autocorrelation, and this is the 21 centimeter galaxy. This is the 21 centimeter shear, and this is galaxy and shear cross correlation. And you can see that from maximum values in these bars, you can see that the SNR actually reduces quite a lot. Obviously, if you observe for a longer time, you can see that these two curves, obviously the cumulative SNR increases if you observe for longer. But here is something we're going to talk about just now, which is the astrophysical foregrounds, which we haven't talked about yet. None of the figures shown before had any foregrounds in them. So what we're going to talk about is the foregrounds. So foregrounds, what they do is they contaminate the large-scale frequency modes, so the small k-parallel modes. So to remove, so what you can do is you have to go beyond the wedge, which we talked about, the foreground wedge. So in our case, what we are trying to do is avoid the foregrounds. And so in that case, we need to avoid small k-parallel. So in our calculations, what we have done is taken k-parallel less than 0.01. We have neglected any of the values of k-parallel less than 0.01. Right. So this is what foregrounds are doing. But what happens is, if you look at the signal to noise plots again, so as I said here, so what you have here is the original plot. So this is 21 galaxy cross correlation. The maximum value is about 120 here. When you do a foreground cut, basically avoiding k-parallel less than 0.01, you can see that the foregrounds, the SNR goes down to about 5. Right? But what you can do is you can also choose an optimum redshift bin. So instead of choosing redshift bins so wide, you can choose finer redshift bins. And you can see that if you do a foreground cut here, that the signal to noise ratio decreases, but it's still not that bad. Right, so this is one of the ways you can mitigate your foregrounds. So basically choosing a different optimum bin, basically optimum finer bin. But what we're going to talk about is something which gives a much better SNR, and that is using a bispectrum. Right, so what we're doing here, we are constructing a bispectrum. So this is including three fluctuations like this. So you take the galaxy and take 2 instances of the 21 centimeter temperature, and this is what you calculate. So that is a bispectrum. Okay, so there is a theory in large scale structure which is known as density modulation. So what it does is when you have a 2 small scale 21 centimeter mode, you are correlating with a long wavelength large scale mode, you can recover some of the line of sight matter modes on large scales. So that is what density modulation does. So this is why the bispectrum becomes important. And as you can see here, you've got the cross correlation between H1 and convergence. So this is from Warren's paper. So H1 and convergence, you can see the maximum value is about 2. But if you look at the bispectrum, which is H1 convergence, the signal to noise actually is not that bad, right? So this is how the bispectrum can actually help in recovering some of the signal to noise. Okay, so again, when we talk about the bispectrum, please don't get daunted by all the equations here. So the interesting thing to note is there's something called the cross-correlation coefficient, which was there in the cross correlations also. So this is just like a stochastic parameter between when you try to measure the 21 centimeter power spectrum and the galaxy density field. Okay, this is something which we can actually measure using the bispectrum. Right, so let's look at some of the plots. So what you have here is H1 galaxy. So this is the SNR for H1 galaxy bispectrum. This is the spectra and the noise. This is for the shear. So this is the 2D pixel SNR for one particular bin. For the shear, the SNR is not that high as compared to galaxy, but it's reasonable. Right. And here I'm going to talk about how the bispectrum basically breaks parameter degeneracies. So I don't have the equations here, but I'm going to tell you how we do it. So we first measure the shear autocorrelation, which can independently measure your sigma 8. Then we measure the galaxy density autocorrelation, which measures the combination of the galaxy bias and sigma 8, but you already have sigma 8 from before, and so you can measure what is the galaxy bias. Then you go to the 21 centimeter autocorrelation, which in the equation, it comes as this combination of cosmological parameters, okay? And if you fix your omega hydrogen, omega H1, you can break the degeneracy between F and BH1, which is the H1 bias, right? And same with the 21 centimeter shear cross correlation, you can do the same. When you look at the galaxy cross correlation, the galaxy cross correlation has these terms coming into the equation. You've already measured what's in the bracket from 21 centimeter autocorrelation. You've measured what is the galaxy bias. You measured what is sigma 8. Then you can measure what is the cross correlation coefficient R21 gal independently. And then if you look at the bispectrum, what you can do is, because the combinations come in differently in the autocorrelation and the bispectrum, you can break the degeneracy between sigma 8 and the combination of omega H1 BH1 and omega H1 F1 and F. So this is basically the steps which we do to break degeneracies between cosmological parameters. And here is a plot of all the different parameters using the different probes. So blue is for only 21 centimeter auto, orange is for bispectrum. You can see that the orange is basically not also doing well, but when you combine the two, then you can get tighter constraints on the various parameters. So the last one is basically all the parameters. So the cross power spectrum, the bispectrum, and all the auto power spectrums included. So that is obviously the most powerful probe to constrain these cosmological parameters. And same you can do for shear. So I'm not going to explain this as, yeah, this is very similar to the galaxy. And then you have the different parameters. So you have omega matter and sigma 8. So again, the different probes you have, the autos, the bispectrum, the auto plus bispectrum, and all the different probes, the auto bispectrum, the cross power spectrum, and the galaxy auto. And then you have Planck in the gray contour. As you can see, obviously the red contours are much tighter compared to any of them. And similarly, you have from the bispectrum, the shear 2121 bispectrum, you have a similar plot. And so what you have here is basically the other cosmological parameters, but they have been separated for the different bins. So here we have taken 8 bins, 8 redshift bins, and we have separated it out. And you can see that the constraints are obviously better at one particular bin. So bin 8, or actually even the other bins are doing quite well with constraining the parameters. So these are the different parameters. This is only for the H1 galaxy. You will have similar plots for shear, which I'm not showing. And then lastly, I'm going to talk about the dark energy parameter constraints. So the dark energy parameter constraints, so you have W0 and WA. These are the dark energy parameters. This is the parameterization equation which we are using. If you take flat W0, WA CDM, so basically, these are the constraints which you get on WA and W0. And you can see that, again, the red contours are doing quite well compared to just the 21 centimeter autopower spectrum. So this one is without the curvature term, and this is if you consider curvature. Right, so you have a lot of different ways to constrain the dark energy parameter. So, so I'm just showing you 2 of the methods, and then I'm going to finish here and just take some questions. So just a summary. So intensity mapping, cross correlations with the large scale structure. So this is basically a robust way to test the cosmological parameters. So when we do the cross power spectrum, you suffer from loss of signal to noise, okay? Because the galaxy and the shear kernels, they fall very quickly in the K parallel space. Then further to the loss of SNR is the challenge from the foregrounds. Because we are trying to avoid the low K parallel modes, you suffer further loss of the signal to noise. If you choose finer redshift bins, it will slightly improve the SNR. But what happens with the bispectrum is the bispectrum helps in recovering the large-scale modes which are lost in foreground removal, basically because of the effect of density modulation. And when you do autocorrelations, combine the autocorrelations with the bispectrum, they help in breaking the degeneracy of cosmological parameters, for example, the F sigma 8 degeneracy, and you can get much tighter constraints on sigma 8 and F. Right, so that is it. And yeah, I'm happy to take any questions you might have, or if you want me to go back. Yeah.
Thanks, Dr. Moumita. Any questions from the audience? We have some time for a few questions. Prof. Ma, please go ahead.
Okay, yes. So yeah, I mean, this formalism extension, you know, is pretty good. But I wonder, because I wonder whether, you know, I wonder the practicality of it, because HIRAX, as you mentioned, is an interferometer. So what you measure is actually the visibility, which is really a convolution of the sky intensity with the 2-dish antenna with a delay factor. How are you going to, if you want to apply this formalism directly, then you have to reconstruct the whole sky, look at the image of the whole sky, and then do the cross correlation, isn't it?
No, we are not. So the measurements from, if you look at the cross correlations from Wiggle Z and GBT, obviously it's not the whole sky, right? You don't need to get the whole sky.
No. That's not what I mean. The GBT is a direct imaging survey of the 21 centimeter intense map. But HIRAX is an interferometry. HIRAX measures the visibility directly. HIRAX does not image the sky directly pixel by pixel. Is that right?
Yes.
So therefore, to apply this formalism, you will have to convert the visibility into the 21 centimeter imaging sky or volume. There is a conversion between the visibility to the imaging of the of the volume, right?
Ultimately,
Because
what
it's
we
not
are
a single.
using, sorry, Inge, ultimately what we are using is not the imaging. We basically need the, we can't convert the visibilities to the fluctuations, right? So the actual fluctuations. So we are interested in the fluctuations. We are doing the cross correlation in the CL space, right? Like in the L space.
Yeah. So I want to know, how are you going to directly correlate visibility with galaxy shear or convergence?
So like so you can, when you get the, you can get say delta T, you can measure delta T, right?
Delta T from what? From
From
interferometry?
the visibilities, right? You can get visibilities converted to CLs, right? And you can get delta T. And then basically delta T is getting convoluted with say the delta G or delta gamma. So that you can do, right?
I don't know, because visibility is a convolution of the total intensity with the beam of with the two beams of the telescope, two dishes, and
Yes.
with a delay factor. And how are you
Yeah.
going to convert that into temperature? I don't know. Yeah.
No, but like that's what you do in CMB also. So what you measure, microwave emission. So basically what you're trying to measure is that, and then from that you can get your like you get your CLs from the map, right? So you get your CLs from your map, and then you can get the fluctuation, and that you can find CMB bispectrum also the same way, right?
Yeah. But this, you don't get a map from HIRAX. You don't, because you only get visibility. It's not an imaging server. HIRAX is not Meerkat. HIRAX is not fast. Fast is one giant dish. It just directly imaging the 21 centimeter sky. But HIRAX is an interferometer. You only measure visibility.
You do the same, like you can do with Meerkat. Meerkat does it, right? So you can do the same. Like when you do cosmology with any radio interferometer, I mean, this is not the first thing. I mean, you can do it with any interferometer also. It doesn't matter if it has to be a...
No.
The scales which you're looking at with single dish and interferometer is just different, right?
Meerkat is using each of the dish as a single antenna, and they just stack 64 dishes image together. So they use as a single antenna, single dish survey. It's a single dish survey mode. It's not interferometer mode. But HIRAX is different. HIRAX is not Meerkat. HIRAX is not fast. It's use interferometer mode. So you don't get image directly. You only get visibility. So here you are forecasting how you would having this three-point correlation function of the H1 galaxy, that you mean the image of the H1, but you don't get H1 directly. You get visibility. So I think a little bit, yeah, there's some conversion in between. Or I see Tony raise a hand. Does Tony want to add something?
I can't see any of the questions. I don't know.
Tony
okay.
is in the participant here. Hello?
Sorry, can you hear me now?
Yes.
Yeah.
Yeah, you can go straight from a visibility to, like, say, a delay power spectrum without going to the image space, right?
Yeah, that's what I thought. So
yeah, so you can just like Fourier transform the frequency direction in your visibility, and then you get something that's analogous to Fourier space, and then you do like a complex conjugate and combine it with the other thing that you're trying to take a cross correlation with. That's how I would have imagined you do it. Like you were saying, you go to the CL space, like you do the combination. You don't do the combination at the level of the image. You don't even have to go. You can go straight from a visibility to like a Fourier space representation of the power spectrum.
Yeah, that's I mean, the thing is, obviously there's no HIRAX data yet, but the thing is, I just looking at the analogy from CMB, you get a CMB map, or even just you can easily go to the CL space. Once you get to the CL space, which you can do for the HIRAX also, right? Once you get to the CL space, you can find out the fluctuations, and then you can correlate with any other field which you want.
Well, this is different from CMB. This is definitely different from CMB. I think I understand what Tony said, but still, I want to see how you achieve this, from the current forecast, because the current forecast is all about imaging, kind of H1 imaging and shear correlation. So I want to see how you would directly from visibility, because that's closer to your eventual data.
Right. Okay.
Yeah, I think
okay,
they use.
Yeah.
Sorry. This M-mode formalism of like Richard Shaw. That's what HIRAX is going to do. So
yeah, that is basically what HIRAX is doing. It's again in the Fourier space, right?
Yeah.
Yeah. So there is a paper by Richard Shaw, and there is another one. I think there's 2 follow-up papers. So that's what we are doing in the pipeline, anyways. So when you simulate, when you're using simulated data.
Which Richard Shaw's paper?
I can. So
one is the spherical interferometer paper, and the other one
exactly.
And the other one is coaxing 21 centimeter fluctuations, polarized scan. Those are the 2 papers.
Is that 2012, 2013 paper, 2014 paper?
Yeah, it's quite old papers. Yeah.
Okay. Yeah.
Okay. There's a question I see in the plots with the redshift bins. Was bin 1 higher or lower redshift? I can't remember where. Is it in the redshift bins? Maybe is it this one you're talking about? Plots with the redshift bin, was bin 1 higher or lower redshift? I'm not sure which.
I think it's about the constraints.
Oh, okay. Sorry. Where is it? Oh, okay. This one, I understand now.
Yeah, this one.
Yeah. So it depends on these are all dependent on your redshift, right? Okay. So I think bin 8 is I think it's the lowest redshift bin, I think. Yeah. So it just depends on how the distribution of the different parameters are with the redshift. Okay. Okay, Tony, is that did you want to ask something, or was it a follow-up thing?
Yeah, I did actually have a question about your other constraints, where you have the dynamical dark energy.
Yeah.
So when you allow for spatial curvature, the bispectrum doesn't improve your dark energy constraints.
No, it doesn't actually. Yeah.
Okay. So what does the curvature constraint look like? Is it just fixed by the Planck, or is it improve the Planck?
Yeah, so you have Planck data. So all of these are with Planck, because if you don't include Planck, then obviously you're not going to get good constraints. Yeah. So sorry, I should have mentioned that.
Okay, and then so does the we're out of time. Looks so the omega k constraint is no better than Planck.
Yeah, no, it's no better than Planck. Yeah, I don't have the table, but I should have put the table up. But yeah, it's not any good better than Planck.
Okay, thanks.
Okay.
Any other questions from the audience? Okay. If not, let's thank the speaker again. Thank you so much, Dr. Moumita.
Thanks, Ajit.
We'll see you all at the next art seminar. Thank you for attending.
Okay. Thank you. Bye.
Thank you. Bye.
Bye.